Hello everyone, I am Karthik, Assistant Professor of Mathematics, SNS College of Engineering. In this lecture video, I will explain about vector calculus and its applications. Okay, what is vector calculus? Vector calculus is a branch of mathematics that deals with the vector fields, which are functions that assigns vector to points in space. And it extends the concepts of calculus from one-dimensional and two-dimensional spaces to higher dimensions. Basics of gradient. The gradient is the fundamental concept in vector calculus that generalizes the notation of the derivative to scalar fields in multiple dimensions. Definition and properties of gradients. The gradient of a scalar field f of n variables is a vector field denoted by del dot f, and it is defined as del dot f equal to dou f by dou x1, dou f by dou x2, etc. dou f by dou xn, where dou f by dou x represents the partial derivative of f with respect to the variable x. Geometric interpretation. The gradient points in the direction of the steepest increase of the scalar field at a given point. The magnitude of the gradient represents the rate of change or slope of the scalar field in the direction. Directional derivative. The directional derivative of a scalar field f in the direction of a unit vector v is given by the dot product of the gradient f and the unit vector d dot f equal to del dot f or del f dot v. This measures how f changes as you move along the direction specified by v. Level sets. Level sets of a scalar field f are the curves or surfaces where the value of f is constant. The gradient is always perpendicular to the level sets of f. Examples of gradient in 2D and 3D. Let us take a first image of a landscape with varying colors to illustrate 2D gradient. In two-dimensional, let us consider the scalar field f of x comma y equal to x square plus y square. Then the gradient is del dot f equal to 2x comma 2y. This means that at any point x y in the plane, the gradient vector points in the direction of the steepest increase of f, and magnitude represents the rate of change of f in the direction. Let us take second and third examples, that is 3D gradient. For 3D gradient, consider the scalar field g of x comma y comma z equal to x square plus z square. Then the gradient del dot g equal to 2x comma 2y comma 2z. Similar to the 2D case, at any point x, y, z in 3D space, the gradient vector points in the direction of the steepest increase of g, and its magnitude represents the rate of change g in that direction. Visualization of gradients with pictures. In 3D space, the level sets of G are concentric spheres centered at the origin. The gradient vector at each point radially outward from the origin, and its magnitude increases with distance from the origin. Visualizing this in 3D can bit or more challenging, but you can imagine a similar concept with concentric spheres expanding outward from the origin, and the gradient vectors pointing outward along the surface of these spheres. Consider the example f of x comma y comma z equal to x square y plus z. First differentiate with respect to f, that is 2xy. Next second term is constant, so that is 0. Next dou f by dou y, which means partial differentiate with respect to y. First term is x square into y. Differentiation of y with respect to y is 1, so which is equal to x square. Third one, dou f by dou x. Partial differentiation of f with respect to z, that is 1. And the gradient is del dot f equal to 2x y I vector plus x square j vector plus k vector. Thank you.